Your furnace stopped at 3 a.m., and you felt it in your bones before you ever opened your eyes. Not the alarm, not a sound, just the slow withdrawal of warmth from every surface in the room, the particular stillness of air that has stopped moving. You pulled the blanket tighter and told yourself it was nothing. By morning, the thermostat read 51 degrees. The repair technician arrived 6 hours later, handed you an invoice for $840, and shrugged like it was the most normal thing in the world. And you paid it. Because what else do you do? Your heat depends on a machine. The machine depends on parts. The parts depend on a supply chain that stretches across 3 continents. And every single link in that chain can fail on the coldest night of the year. This is the architecture of modern heating. A system designed not to last, but to be serviced. What almost no one building homes today will tell you is that a method perfected by Achaemenid Persian builders more than 2,500 years ago eliminates every single one of those failure points, using nothing but the ground beneath your feet, water, and your own hands. The forced air heating system became the default in North American residential construction after World War II, and the industry has defended that default ever since. Here's the flaw baked into the design. Forced air systems heat air, not walls, not floors, not the structural mass of the building itself. Just the moving column of air that cycles through your ducts, warms you briefly, and then loses roughly 30% of its energy to duct leakage before it ever reaches the room, according to the U.S. Department of Energy. You are paying to heat your attic and your crawl space. The moment the blower stops, the air cools in minutes. The building has stored nothing. It holds nothing. It is, thermally speaking, a tent with better drywall. The system was never designed to retain heat. It was designed to sell you more of it. Persian engineers working under the Achaemenid Empire. The civilization that built Persepolis, engineered the Connaught underground water systems, and mastered passive climate control across one of the most temperatured extreme landscapes on Earth, understood something that modern construction forgot. They built with cob, a dense, hand-formed mixture of subsoil clay, sand, and straw that behaves not like a barrier against temperature, but like a reservoir for it. Their structures in the high Iranian plateau endured days exceeding 100 degrees Fahrenheit and nights dropping below freezing, with no fuel, no machinery, and no maintenance contracts. The walls did the work. Heat doesn't disappear when your fire goes out. It hides. Every material around you is either storing thermal energy or releasing it. And the speed at which it does that is measured by a property called specific heat capacity, which is simply how much energy a material can absorb before its surface temperature changes. Stone, water, dense clay, high specific heat capacity. They absorb a large amount of heat before they feel warm to the touch, and they release that heat slowly long after the heat source is gone. Lightweight timber framing, fiberglass insulation, drywall, low specific heat capacity. They warm fast and cool fast, which is why a conventional home feels frigid within an hour of the heating system shutting off. Cob sits in a different category entirely. Its clay matrix, when mixed at the correct ratio, achieves a thermal mass, meaning the total heat storage capacity of the wall system, that can buffer indoor temperatures for 8 to 12 hours without any active heat input. The wall becomes the heater. The sun charges it through south-facing glass during the day, and the wall discharges that stored energy through the night. Passive solar combined with thermal mass is not a modern green building idea. It is a 2,500-year-old engineering solution that the industry quietly abandoned when gas got cheap. Think about a cast iron skillet pulled off a gas flame. You turn off the burner and walk away, but the skillet keeps cooking. 15 minutes later, you can still sear a steak on its surface. The pan absorbed heat energy into its dense iron mass. And it releases that energy gradually, on its own schedule, without any continued fuel input. A correctly built cob wall works identically, except the skillet weighs a few pounds and a cob wall weighs several tons. The mass is the mechanism. The release is the result. The reason cob completes what thermal mass alone cannot is its material composition. A standard cob mix is roughly 70% subsoil, which itself is typically 20 to 30% clay content, combined with sharp sand at a ratio of about 1 part clay soil to 1.5 parts sand, with chopped straw woven throughout as a tensile fiber network. That straw is doing something structural engineers now describe formally as fiber reinforcement, the same principle used in steel-reinforced concrete, except the fibers are biological, biodegradable, and free. But here is the property that separates cob from concrete and brick in a living home. Cob is vapor permeable. It breathes. It absorbs excess moisture from the air when humidity rises and releases it when the air dries, regulating interior relative humidity between approximately 45 and 65% without any mechanical ventilation. The American Society of Heating, Refrigerating and Air Conditioning Engineers, ASHRAE, identifies that 40 to 60% relative humidity range is the optimal zone for both human respiratory health and the inhibition of mold growth. Cob hits that target passively, all day, every day, for the life of the building. The three materials in a cob mix are subsoil clay, sharp sand, and straw. And in most regions of North America, Europe, and Australia, at least two of the three are either free or nearly free. The subsoil is what comes out of the ground when you dig a foundation. It is typically discarded as waste on conventional construction sites. Sharp sand, meaning coarse, angular sand, not fine beach sand, runs between $20 and $40 per cubic yard from any landscape supplier. Wheat or barley straw costs roughly $8 to $12 per bale, and one bale covers a significant volume of mix. You are not buying a building material. You are assembling one from what the land already offers. The first step is a subsoil test. Take a handful of your excavated subsoil, wet it until it clumps, and roll it into a ribbon between your fingers. If the ribbon holds for 2 to 3 centimeters before it cracks, your clay content is in the workable range of 15 to 30%. Too crumbly means not enough clay. Add purchased dry clay powder until the ribbon holds. Too plastic and sticky. The ribbon stretches past 5 centimeters without breaking, means excess clay. Correct with additional sharp sand. On ink, this test costs nothing and takes 4 minutes. The second step is building your test mix. Combine your subsoil and sharp sand at that foundational 1 to 1.5 ratio by volume. Add water gradually until the mass holds its shape without crumbling, then fold and chop straw at approximately 1 part straw to 6 parts combined soil sand mix. Blend by foot. Traditional cob mixing is done by treading the mass on a tarp for a minimum of 20 minutes until the straw is uniformly distributed and no dry pockets remain. The third step is the test ball. Form a fist-sized sphere of your mix and let it dry for 24 hours in open air. Drop it from chest height onto a hard surface. If it holds its shape, your mix is correct. If it shatters, you need more clay. If it deforms without cracking, you need more sand. Do not skip this step. Building with an uncalibrated mix wastes both time and material, and a wall with excess clay content will crack during drying. The fourth step is placement for thermal mass effect. For a cob wall to perform as a thermal battery, it must be positioned on the interior side of your insulation layer. Or better, as a freestanding interior thermal mass wall within a south-facing room. Walls exposed to direct winter sun through glass for 6 or more hours daily will absorb sufficient energy to radiate through the night. Build your cob in lifts, horizontal layers, no more than 30 centimeters deep per session, and allow each lift to firm up for 24 to 48 hours before adding the next. This is not slowness. This is the drying chemistry working correctly. The fifth step is roof overhang calibration. A cob wall's thermal performance depends on sun reaching the wall in winter and being blocked in summer. Using a sun angle calculator for your latitude, design your south-facing roof overhang so that the winter sun angle, typically 20 to 35 degrees above the horizon in northern temperate climates, strikes the full face of the thermal mass wall, while the summer sun angle, 55 to 70 degrees, is blocked by the overhang. This geometry is fixed physics, and it works without moving parts. The sixth step is the finish render. Apply a final coat of hydraulic lime render, a mix of natural lime and fine sand, approximately 12 to 20 millimeters thick across the exterior face of the cob. Lime is naturally antimicrobial, allows the wall to continue breathing, and protects against rain erosion. Apply it in 2 coats with a minimum of 48 hours between applications. Keep the freshly rendered wall shaded and lightly misted for 3 days during curing to prevent surface crazing. Rapid drying causes the surface to crack before the bond fully develops. Monitored cob structures in temperate UK climates, documented by the University of Plymouth's Centre for Earth and Architecture, maintained interior temperatures within a 4 to 6 degrees Celsius band across a full 24-hour cycle, even when external temperatures swung by 18 degrees. And that is thermal stability your forced air system is physically incapable of delivering, because it responds to temperature rather than preventing its variation. The wall does not react to cold. It resists it continuously from the moment the sun sets until it rises again. Now set that against cost. A conventional timber frame home insulated to code with fiberglass batts and a gas forced air system runs between $90 and $140 per square foot for the thermal envelope and HVAC combined, not including fuel costs over the life of the building. A cob wall system, including labor for an owner builder, typically runs between $8 and $15 per square foot when subsoil is sourced on site. Over a 30-year period, with average U.S. residential heating costs running at approximately $900 per year, the conventional system costs a homeowner roughly $27,000 in fuel alone, a cost the cob thermal mass wall reduces to near zero for passive solar gain during daylight hours. The gap is not marginal, it is generational. The people who already know this are not a fringe. The natural building movement has been tracking owner-built cob structures since the 1990s, and the number of permitted cob homes in Oregon, California, and the UK has grown steadily. Builders like Seren Vos, a Welsh owner-builder who completed a 900-square-foot cob home in 2021, document interior winter temperatures holding above 17 degrees Celsius through nights that dropped to -4 degrees Celsius outside. With no supplemental heat source beyond a small wood stove. The knowledge exists. The track record exists. What doesn't exist is any financial incentive for the industry to tell you about it. Every winter, the supply chain that feeds your furnace gets one link shorter. Parts suppliers consolidate. Technicians retire. Fuel prices move on variables you will never control. The cob wall you build this year is still working in 200 years, in a grid-down scenario, in a fuel shortage. In any world where the machines stop. You can keep feeding a system designed to fail, or you can build a wall that heats itself. One of those decisions belongs to the industry. The other one belongs to you. Your move.